In the previous video, we have seen a theoretical property that is interesting to consider when you want to make your fixed point computation a little bit lighter and to avoid executing twice a constraint if it's not necessary. Here we will see another technique that you can implement in your solver to make the fixed point computation also a little bit lighter. And it's especially useful when you have very small constraints. And in fact, we will try to bypass the fixed point computation to update some of the variables in that case, if we would let it propagate through the fixed point, for instance. That's called domain views. The constraint that we consider, the very small constraint that we'll consider, will be of this type. You have a variable x, which is equal to another variable plus an offset. Okay, for instance, this might be the value 2. Okay, so it's an integer, or it's an integer. Or you might say the variable x is equal to the opposite of the variable y. Or you might have a scaling, an integer scaling. So again, this might be, for instance, the value 2. So x is equal to 2 times the variable y. For this very small constraint, what can we do? Of course, one possibility is to extend the constraint interface or the abstract class and implement the propagate method, implement the propagate filtering algorithm for this small constraint. That's quite easy, but there is a big disadvantage with such an architecture of implementing such small constraint and let them propagate through the fixed point. This is your domain store. Okay, this is your domain store, and I will assume that in my constraint store, I have 3 constraints here. As you can see, we have this small constraint that y is equal to x plus 2. So that's one of the small constraints that I just have mentioned in the slide before. Okay, and we have that y should be different from z. Let's assume that the value 2 was just removed from the domain of x. Okay, and let's assume that we propagate the constraint c3 is different, c3, so y is different from z. Clearly, we see that we have 2 values there, so we are not able to remove anything according to the semantic of that constraint. Okay, so there is nothing to filter for y different from z if we consider this constraint. But if we would have considered c1 first, then we would be able to do some filtering on the domain of y, because if 2 has been removed from x, because of that constraint, we know that 4 will not be part of the solution there. And so if we would have executed this constraint first, and then that one, then we would be able to remove the value 3 from the domain of z as well. Okay? And so you see that the fixed point computation was a little bit too long because we have considered first this one and then this one, okay? While the good choice was to do it in the opposite way, so this one first and then this one, okay? So the goal there, because of this problem, we will try to have a design for this very light constraint that will avoid to be scheduled in the fixed point computation. The idea is to modify a little bit the architecture. So we have in the architecture, we have the int-var interface that you are familiar with, okay? And you have, of course, the implementation of this interface, okay, which is called the int-var implementation class. Now we will introduce 3 new implementations. We will introduce one implementation for the multiplicative view, one implementation for the offset view, and one implementation for the opposite view. And because they all implement int-vars, they will be considered as integer variables, and you can use them inside your models or inside your propagators. You can do everything you can do with a standard variable because you really implement this int-var interface. But in terms of implementation, you will see that what we do is an idea that is also used by databases, for instance. When you have a database, you can also create a view, a light view on some tables. That's exactly the same idea that we will use here. So let's see now how to create a view on a variable. So we have this situation. We have a domain for the variable x, which is 0 up to 9. And we would like to create a view -2 times x minus 1. We have already implemented inside the factory method of minicp the methods minus, opposite, and mul that allows you to create easily the offset view, the multiplicative view, and the opposite view that we have shown just before in the architecture. Okay, so the factory method will instantiate this class for you. And so to create this view, the first thing that we need to do is multiply it by 2, because the offset view requires that A is a positive number. So we multiply by 2. That's the first thing that we do there. And so we call the mul method of our factory with the parameter 2 to compute 2 times x. Then the next thing that we do is need to apply the minus there. So we do opposite there, okay, to get the minus 2 times x. And then at the end, we do an offset view of -1. This is what we do there, and it's represented there. So as you see, every time we create a new view, we do a wrapper on the previous view, and so we will wrap it 3 times in that case to express this expression. And once it's done, you can really manipulate this variable y as a standard variable, okay? If you would use it inside the constraint doesn't know that it's a view, and it's not really an implementation as this one, okay? So these one are really views. And so if you ask for the minimum of the domain of y, what you would get is a minus 19, because you would get, because of the minus, 2 times minus 9, so minus 18, minus 1 there, which is minus 19 as you would expect. Okay, you can also remove values from the domain of the variable of the view. So the implementation now, as we said, as we announced in the class diagram, we will implement the invar interface. And internally, that's the one of the offset, right? That's the one that corresponds to y is equal to x plus some offset. So, of course, I do not present the constructor, but I initialize properly the variable x and the offset constant. If you ask for the minimum of the domain, what I will return is the minimum of the domain of x plus the offset. If you want to propagate this constraint on any change of the domain of the variable x, because it's a functional view, I can delegate this and say, please, constraint x, would you be able to call this constraint c on any change of the domain? Okay, and so this is what you will do as well. Is fixed, you clearly delegate it to x is fixed, so the view on y will be fixed if and only if the view of the variable x is fixed as well. And in terms of contains, you need to remove the offset. Okay, so the value v is contained in y if v minus the offset is contained in x. And that's the same for the removal. Prior to removing from x, you just remove the offset value on it. Okay, so that's a delegate pattern here that we do on the variable x. And as you know, x might be of type invar impl. Okay, it's possible that it's an invar impl. But if we wrap a view on another view, this might also be a view. Okay, this might also be a view as well, this variable x, you don't know.